Welcome to Unit 7, Inference for Quantitative Data, what an emphasis on means. This is a special topic, 7.5. This is really just an extension of topic 7.5 over a matched pairs t-test. Now back in 7.4 and 7.5, I did mention and talk about a matched pairs t-test, but I can't emphasize how important this special type of test is. So that's why I've made a whole separate video of it, just to make sure that everybody completely understands it. So let's first talk about what exactly a matched pair t-test is. A matched pair t-test is a special type of one sample t-test for the mean difference of data collected with pairs. The key in here is that there is one sample of data that is simply measured in two ways. So it will often look like there's two samples of data, but it is not. In the upcoming topics, 7.6, 7.7, 7.8, and 7.9, we are going to examine the difference between two samples. That's comparing the mean between two samples, the mean from one sample and the mean from a totally separate sample. Now, we're not doing that here, but oftentimes it looks like you have two samples. The key here is to read the problem very carefully and realize that there's really only one sample that was simply measured in two ways. Some pretty famous examples of this that I've seen in the past with the AP test is data from twins. So maybe we look at 20 sets of twins and we measure each twin. So we have one set of 20 twins, one sample of data, and we're going to look at the difference between two twins. And that's oftentimes a great pair because twins are very, very similar. So looking at the few differences between them is something that researchers often do. Before and after data. So if I have one sample of people and I measure them before and then I do something to them, maybe it's a training program or a pill or who knows, and then I measure them a second time after. Measure twice data. What I'm talking about here is maybe we have one set of objects, but we measure them twice. An example in the past I've seen with this was that they actually had meat that they were testing for E. coli, and they were testing each chunk of meat with two different methods, and they wanted to see if there was a difference between the two methods. So there were two methods, but there's only one sample of meat, and every single sample got tested each way. So we had two sets of data, but they came from the two different ways of measuring. Also, any data that's collected from a matched pairs experiment is always going to be examined through a matched pairs t-test. So remember, if you're reading an experiment and you have a group of people and they're paired together, so two people are paired together, and you're going to give one person treatment 1, the other person treatment 2, or maybe you're going to pair one person up with themselves. Give their left arm treatment 1, give their right arm treatment 2. And again, what we care about in any of these matched pairs experiments is the difference that exists between each pair. So we actually don't care about what each person got, we care about the difference in each pair. So at the end of the day, all we care about is the differences. So that's essentially the sign of a matched pair t-test. Yes, you got two samples, but you don't care about the two samples. Excuse me. You have one sample, two sets of data from that one sample. But instead of caring about those two sets of data, we only care about the difference produced from each individual within that sample. Here's a couple more examples that I've actually seen before. Measurements of weight taken before and after a 2-year training program for a random sample of 100 people. So there's that before and after program I was talking about. So we measured their weight before, then after a 2-year program, we measured their weight after, and we did that to see the difference for each person. So each individual is going to have two measurements, before and after, and all we care about is the difference between those measurements. Measurements of weight for each twin. This is an example of the twins, right? So we have 100 pairs of twins, and we're going to look at the difference in the weights between each pair. So we're going to have essentially 200 measurements, 100 of the one twin, 100 of the other twin, but we don't care about that. We care about the differences. We care about the 100 differences between each pair of twins. Third example is measurements of weight for both individuals in pairs formed by matching 100 people from state A and 100 people from state B. based on exercise habits, education level, gender, age. So remember, when we create pairs, we put two people together that are very similar. So we got a person from state A and a person from state B, and we match them together because they both exercise a lot, they both have high levels of education, they're both men, and they're both about 40 years old. That's a great pair, and we're going to do that with all 100 people, right? Everybody's going to be paired with somebody just like them, and then we're going to match their weights. We're going to look at the difference of their weights, because the idea here is if all these other variables are the same, what we're focusing on is, does the state they live in matter? Like, are people from state A heavier than people from state B? And, it doesn't matter. They're the same age, the same gender, the same education level, same exercise habits, yet they weigh different. What's that about? So again, we have one set of data and we're looking at the differences. And finally, an example is measurements of weight recorded for both spouses of 100 randomly selected married couples. Now, married couples are not twins, but married couples are oftentimes good matched pairs because two people get married because they have a lot of similarities. They love each other. They have something in common. So looking at the difference between them is important as well. So I hope by now you are getting an understanding of what we're looking at. And the one thing I want you to understand is we never make pairs based on randomness. We never say, oh, I'm going to pair you up with Joe just because I randomly picked Joe to make your pair. No, pairs are put together for important reasons. Maybe you're twins. Maybe your spouses, your husband and wife, or maybe you have a lot in common with that person that you got paired with. All right, so let's get back to actually how to do this. So once you've officially identified a situation as a matched pair t-test for the difference between measurements, you must create a single list of the differences between the pairs. You will follow the steps of a one-sample t-test focusing on the mean difference. So keep in mind, we're trying to find the true mean difference. Well, we don't know that, right? We're trying to find it. We don't know what that is. What we do have is a mean of all of our differences in our sample, and we have a standard deviation of all those differences. Those are the two numbers, and to be honest, those are really the only two numbers you need to be able to solve one of these problems. So we attach that little subscript DIFF to focus that this is a difference, right? We're looking at the difference between two sets of data, and that all we really care about at the end is that one list of differences, and we're going to get a mean of all those differences. We're going to get a standard deviation of all those differences. All right, let's go through the 4 steps of the test that you should already know very, very well. All right, step 1 is to name and give the hypotheses. So make sure the name of this is a one sample paired t-test for the mean difference between, and then you'd say between the before and the after, or between the two pairs of twins, whatever. You got to add a little bit of context there. Now, the null is always going to be that the mean difference is equal to 0, because you always start off assuming, oh, there's no difference between those twins. Oh, there's no difference between the before weight and the after weight. Oh, there's no difference between those spouses. So understanding that, you're talking about the mean difference being 0 is the null, because we always think otherwise. We always think that there is a difference. We always say, no, one twin, the first twin weighs more. That's my belief. Or husbands make more money maybe than their wives. Or this particular method of measuring E. coli from a chunk of meat is different than this other one. So we always have to start off by assuming that there is no difference. There is no difference between these things that you're looking at. And then the alternative is that, no, there really is a difference. And it could be a greater difference. It could be a less than difference. Or maybe you don't even care. You just care that there is a difference. So you kind of have 3 options there for that alternative. But we're always focusing on 0 because the null would say, there is no difference at all. And then the alternative is us trying to find out if there is. All right, step 2 should sound pretty familiar. We're going to check those conditions, and we're going to build a sampling distribution on the assumption that the null hypothesis is true. So, of course, the sample must be random to avoid bias. Now, sometimes in an experiment, we do use volunteers, but there has to be random assignment, meaning what person in the pair gets treatment 1, which gets treatment 2. That has to be random, and that's still okay to meet that random condition. The sample must be less than 10% of the population it was selected from to assume independence. And remember, we have to be big enough. So if the sample size is 30 or greater, boom, we're already big enough. It's nice and easy. But if it's not, if we're under 30, we do have to kind of examine our data and make sure there's no major outliers and no major skewness. And that is so that we can use a t-model. So remember, why are we using a t-model here? Because, of course, we only know the standard deviation of our sample, which is going to cause us to have to use standard error here. So the sampling distribution, the mean of all, remember, please remember what a sampling distribution represents. It doesn't just represent your one difference, it represents all possible mean differences. But if we're assuming the null is true, that means there should be a 0 in the middle. If we're going to assume there really is no difference, then the mean of all possible differences should be 0. And then the standard error of that sampling distribution is going to be taking the standard deviation of our sample, the standard deviation of our differences, divided by the square root of n. Now remember, there's really only one sample, so the degrees of freedom, df, is going to be your sample size minus 1 still, so that way we know which t-model to use. All right, step 3 is finding the t-score and the p-value. So the t-score is now we're going to take our difference. What was the observed difference that we saw of our differences? What was the mean of our differences? And we're going to subtract the null, which we're assuming there was no difference, and we're going to divide by that standard error. That will tell us where we are, and with that number alone, you could usually get a good idea if you're significant or not. But we do have to find that p-value, which is, of course, the probability that any other difference is more extreme than ours, or yours, as I wrote here. Now, remember, I used a greater than sign. If we're looking at a difference being less than 0, then you'd use a less than sign, because obviously that's negative, and we want to be even more negative. And again, that's the probability, right? That's the p-value, the probability that any other difference is more extreme than yours, assuming the null is true, which is, of course, what we're doing here. So then we're going to actually need the t-score to do that, because our calculator doesn't understand mean of anything. It represents t-scores and z-scores. So then we're going to find the probability that t-score is greater than ours, and then we're going to use TCDF to do that. Now, don't forget, when you do go to TCDF, you will need the degrees of freedom, which, one more time, is your sample size minus 1. Then we have to make a conclusion. And my goodness, by now, I hope that this is very simple to understand. If the p-value is less than your significance level, remember your significance level is your alpha, which is typically 1% or 5%. So if your p-value is less than your significance level, this means that what you observed is significant, that the null should be rejected. And there is significant evidence that the alternative hypothesis is true. If the p-value is more than your significance level, this means that what you observed is not significant and that we fail to reject the null. So it just means that what we observed was not anything weird on the assumption that there really is no difference. So there is no significant evidence that the alternative hypothesis is true. Please remember, for maybe the 5th or 6th time, we never ever say that the null is true. We just do not have enough evidence to go with the alternative. All right. Now I want to jump into 2 examples, and they're 2 really good examples. I'd appreciate if you take the time to listen to them both and see all of my beautiful, wonderful work for them. That way you really get a good feel of what these examples look like. So here's the first one. A consumer advocate group wanted to see if car dealerships around the state of Texas give different prices to males versus females. So are they being sexist? Are they giving different prices to males and females when you're going to buy a car? So they randomly pick 10 car dealerships from Texas, and what they do is they send a male and a female to go into that dealership and inquire about the same type of car and see what price they would be told. So this was repeated for each of the 10 dealerships. So the idea here is that I only have a sample of 10 dealerships, but I measure each dealership twice. I measure how much they would charge a female for a car and how much they would charge a male for the same car. So this is a great example of one that, initially someone might look at this and think, oh, 2 samples, males and females. No, it's really 1 samples. And we looked at dealerships. We actually didn't look at males and females. We looked at dealerships. And at each dealership, we asked, what would they charge a male? What would they charge a female? So the question is there strong statistical evidence that on average females are given higher prices than males? Okay, so what I actually did for you in this chart is I actually found those differences for you. I'll be honest, that's not always done for you, okay? Sometimes you have to find those differences on your own, and it's just as simple as taking the female price minus the male price. So for example, dealership 1, the female was charged $400 more. Dealership 2 was a tie. Dealership 2 was very fair. Dealership 3, the male or the female was charged $1,100 more. Dealership 4, the female was charged $350 more. Dealership 5, they charged the male more. There was a negative difference. You do have to go in the same order. So I'm doing female minus male. And then you can obviously see the rest of the numbers along the way here. Now, I do want to show you, at the end of the day, you do need to get the mean difference, right? You do need to get the mean difference and you need to get the standard deviation of the differences. So let me just show you a couple things here on your calculator that's pretty cool here. So one thing you could do is you could just find the differences on your own, or maybe that's super nice like this and a problem those differences are given to you. In that case, all you got to do is make a list of the differences. I believe I have them here in list 3. So in list 3, I've listed all the differences: 400, 0, 1,100, yada, yada, yada. Now, the other thing you could do, especially if the differences are not given to you, you could type the prices in 2 separate lists. So in list 1, I have the female prices. In list 2, I have the male prices. So if the differences are not directly given to you, one quick way to find them is this. Again, type the females in list 1, males in list 2. Then when you go to your home screen, you do second list 1 minus second list 2. You literally ask the calculator to subtract the 2 lists. And as long as you type them in correctly where they're all matched up, it'll get you the differences for you. And then you can actually just hit store, which is the button right above on, and store that as list 3, and it'll put all those differences into list 3 for you. So again, you could create that list of differences on your own, just put it in the list, or you could have the calculator do it for you. But at the end of the day, I now need to go and ask the calculator to run a one variable stats on list 3. And there is the mean difference. So the mean difference was $85. That's positive. That means on average, the females were charged $85 more than the males. And the standard deviation I need as well, 573.0280. All right, now I'm ready to go. So step 1, name and hypotheses. This is a one sample paired t-test for the difference, the mean difference between the price a female is given for a car and a male is given for a car at dealerships in Texas. So my null would be, oh, there's no mean difference. There is no true mean difference. You might have saw a difference between your sample, but truthfully, there is no difference. Males and females are charged the same. And the alternative is what we're wondering. We're wondering, are females truly charged more? So we're wondering, is there a greater difference? Because we did females minus males, and that would be, if females are charged more, that would be a positive difference. All right, so the sample of 10 dealerships was random to avoid bias. 10 dealerships, clearly under 10% of all car dealerships in Texas, to assume independence. The sample of 10 is not big enough, so I do have to check my data, so it's worth us just going over that again. So to check your data real quick, remember it's in list 3, so I'm going to hit second y equals. Go to my plot 1, make sure it's on, make sure this little histogram is highlighted there, and then type the appropriate list, which is list 3 for me. And then you can exit out of there. And remember, zoom 9, that's your zoom statistics, to zoom on your stats. And I mean, it doesn't look great, but there's only 10 values. I certainly don't see any major skewness, nor do I see any major outliers. So we are safe to use a t-distribution with 9 degrees of freedom. All right, so I have to assume that the null is true, that there is no difference. So the center of the sampling distribution will be 0. And the whole reason why I have to use a t-model is because I'm using the standard deviation from my sample, which is 573.028. And I'm going to divide that by the square root of my sample size 10 to get my standard error, 181.207. All right, now my t-score is saying, all right, my difference, the difference I saw in my sample, my mean difference was, sorry for this poor handwriting, was 85. My computer doesn't do a great job of sensing that. All right, was $85. So now the question is that significant? It certainly doesn't seem like it. $85 doesn't seem like a big difference, but you never know, right? So I got to figure out, where does $85 fall on my model that centers at 0? Because there should be no difference, right? So I take 85 minus 0, divide by my standard error, and I get 0.4691. That is a very small t-score. That means I am barely above the mean. So I'm really not that far away from 0. That tells me right away that this is probably not significant at all, and that females are not necessarily charged more. Yes, I did see an $85 mean, but who knows? So that's where we're going to actually find the p-value, which actually makes some sense here. The p-value, the probability that any other difference is more than my $85 difference, which is the probability that a t-score is more than my t-score of 0.4691. Use TCF on my calculator to find that. I'm going to go from my t-score to 99. I'm going to use infinity, but on my calculator it's 99. And then I need another comma there with the degrees of freedom. And I'm going to just show you that real quick so everybody knows where that's at. Second vars, go and grab TCDF number 6 here. Oh, I went too far, sorry. Number 6. All right, and then I'm going to go from the 0.4691. Having some technical difficulties here. 0.4691, and again I'm going to go to 91, and let's see here, I need 9 degrees of freedom, and that's where I got the 0.3251. So that's very likely. That's a very high p-value. That means that my difference of $85 or even higher was actually not that weird. It was not that significant, assuming that the null is true, that there is no difference. So that gives me a pretty easy conclusion. Since my p-value of 0.3251 is well greater than any level of significance, including 0.05, I will fail to reject the null. There is no significant evidence that a car dealership in Texas charges females more on average than males. So good to go. No sexist treatment going on there at car dealerships in Texas. All right, example 2. Makers of a new skin healing ointment want to determine if their new ointment heals wounds faster than nothing at all. So 8 volunteers are used in the study. Each volunteer is given a similar cut on each of their forearms, right and left. Then for each subject, it is randomly selected which cut, left forehand or right forehand, gets the new ointment and which gets nothing. Once all subjects have the ointment on one cut and none on the other, they will wait and see how many days until the cut is completely healed. On the next page is the data from this experiment. So this is clearly a matched pairs experiment. Each person was paired with themselves. Left arm got something, right arm got something else. In this case, one arm got the ointment on the cut, the other arm did not get the ointment. So is there significant evidence that the mean time to heal a cut is shorter with the new ointment at the 1% significance level? All right, so here are my 8 subjects, and we have the number of days that the cut healed with the ointment and the number of days that the cut healed without the ointment. Now notice I did not give you the differences, and I do need to get that list of differences. But for an example like this with whole numbers, my goodness, it's pretty easy. So let's just do with the ointment minus no ointment. So we got -2, -3 days, 0, -3, -3, -4, -2, and -5. So other than one subject had the same heal time for both arms, 0, so that's why difference of 0, but everybody else had the cut with the ointment heal faster. So again, now I need to get the mean and the standard deviation. So I'm going to go to my calculator, stat edit, and I already have these entered into list 4. So there's my, and I don't, because it's so easy to do the subtraction, I'm just going to enter them into my list. And then I'm going to run a 1 variable stats for list 4 where my differences are. And I get a mean difference of -2.75. So on average, the wound healed faster by 2.75 days, but there was a standard deviation of 1.4880. And those are the numbers I'm going to need to solve this problem. So the name and the hypotheses. So this is a 1 sample pair t-test for the mean difference between the time for a wound to heal with the new ointment and the time for a wound to heal with the without ointment. The null would be, there's no difference. The new ointment, it doesn't matter. There's no difference. That would be 0. And I'm hoping for a shorter difference. Remember, I subtracted in a way that's giving me negative numbers. I'm hoping for there to be a shorter amount of time with the ointment, which would be value less than 0. So 8 volunteers, but which arm got the ointment was random. So there's that randomness to avoid bias. The sample of 8 people is less than 10% of all people to assume independence. Now 8 is not big enough. So once again, I got to look at my data. So remember, this was list 4. So I'm going to go to my plot. Make sure you change the data to list 4 for me, at least. And then exit out of there and do the zoom 9. And again, no major skewness, no major outliers. You could argue and say that looks like something, but again, it's only 8 values, so it really doesn't look like much. If you don't see any major outliers, any major skewness, you're good to go. So we are going to use a t-distribution with 7 degrees of freedom. So now remember that sampling distribution has to be built on the assumption that the null is true. So I'm going to assume that the mean of all differences, not just mine, the mean of all differences is 0. Some differences will be positive, some differences will be negative, but the mean is 0. There's truly no difference, right? And then the standard error, which is again why I'm using a t-distribution, takes the standard deviation of my differences and it divides it by the square root of my sample size 8 to get 0.5261. And then now I have to find my t-score. So my t-score is, where is my difference located? Now remember, our difference from our calculator was negative 2.75. So I'm going to take my difference minus my mean difference minus 0, because I'm assuming there was no difference, that was the null, and divide it by my standard error, and I get a very low t-score, negative 5.2271. That already is making me wonder, or making me think that this is significant. So now the p-value is the probability that any other average difference is lower than my negative 2.75, and that would be a t-score lower than the negative 5.2271. So I used TCDF. This time I had to start with the negative 99 to go way below, and don't forget the 7 degrees of freedom, and I got a p-value of 0.000608. So that's a very low number, which means that, essentially I should not have seen what I saw. Seeing a difference of negative 2.75 or lower should not have happened, but guess what? It did. So that's what tells me that this is certainly significant. So since my p-value, and I forgot my less than sign, is less than 0.01, I will reject the null. There is significant evidence that the mean difference in time for a wound to heal with the new ointment is less than 0. So my conclusion is that the new ointment is faster at healing wounds. So awesome, awesome, awesome. There is evidence that the new ointment works to heal wounds faster than nothing. So give a nice conclusion there in context, please. I'm actually going to give you a bonus question here. Obviously, we're getting closer to the AP test. So this would be a great time on the AP test in the middle of a question like this to go and see if you understand something that we learned a long time ago with experiments. So it says, should a placebo have been used? Now remember, each subject got the ointment on one arm and nothing on the other. Should we have put something on that other arm? Maybe just like a moisturizer of some type, something. And the answer is, when you're working with people, yeah, you probably should. Because, and this is going to sound weird, but this is true. If I know that one arm has ointment and the other arm has nothing, I might protect that one arm. I might protect that one arm with the ointment because I don't want it to get injured. I don't want anything to happen to it. Or I know that, or you know what else might happen is, if I have ointment on one arm, I might not protect that arm because I got ointment on it, right? And it's the other arm that doesn't have ointment that I protect. And maybe because I'm protecting that arm, it heals faster. That's the whole point when you're working with people, is when they know that they're not getting something, or they know that one arm is not getting something, they might treat it differently. And that could create a difference that we don't want. We want the sole difference to be the ointment. So to be honest, the placebo should probably have been used here, because anytime you're working with people and you're going to give one group something and another group nothing, you need the group that gives nothing. You got to give them something so that they think they're getting something, because if you don't, then you create the placebo effect. So anyway, just a side question, especially as we're starting to prepare for the AP test sooner than later. All right, guys, that's it. Hopefully you enjoyed the lesson.